So open. All right, not a whole lot new stuff here. There were two new PRs that I saw this week. One was for me. That was a result of the collaborative work that Radek and I did, looking at trying to make buffer list appends faster. And we kind of ended up with two complementary changes that I think are both worth doing, but this is only the first one, which is a smaller change. This basically changes it so that in refill append space, we dynamically change the length of the append buffer that we're adding based on how big the old one was. So basically, this is kind of like in C++ where vectors grow. They double each time. That's more or less the same thing we're doing here. We do bound it, but the end result is that hopefully we're doing that much less often if we have really big buffers that have a lot of appends happening. And it seems to help fairly significantly. The only interesting thing is that tcmalloc actually ends up slowing down at some point when you have larger append sizes. And I don't know why exactly. It changes depending on how we tweak different things. But it consistently, we seem to hit it sooner or later. So overall, it still seems to be better than what we have in master, though. Far better, especially for append hole. With the ring buffer, it's even better yet, especially when we stay within the ring buffer and don't kind of go outside of it. We can if we have too many buffer lists at once still in memory. But it overall, the combination of the two, at least according to our micro benchmarks, looks really good. In practice, I see a lot less tcmalloc overhead, but it's not really speeding things up yet, as far as I can tell, at least in our test case with the MDS. So anyway, that's kind of where that is at. I guess I just went over the whole thing, but that's that. Any questions or thoughts on that PR? One thing I am curious about, Casey, do you guys use any of the Dank framework in RGW yet?
Not directly, I don't think.
Okay. So this may actually help if you guys have any cases where you're doing like append hole and lots of little appends. I don't know if you do, but that was what we were noticing in the MBS, is that it was doing a lot of it. And they weren't using Dank, which kind of also fixes this, but just in a different way. All right. Well, next PR that I've got for new PRs is one from Jan, and this is shoring up some of the ephemeral pinning work that just went in a little while ago. The idea here is to distribute dirfrags. So that's kind of like what I was doing with the pre-sharding and pre-distribution of dirfrags, but they're doing it for ephemeral pinning. And theoretically, I guess that the idea here is that we're going to reduce the number of subtrees because of it. So anyway, need to see how that works, see if it works well or not. And that was it for new PRs. Updated, I think Adam and I both agree that we should use the Majian-Peng's PR to avoid flushing too much data at once in BlueRock's environment that needs QA. Hopefully Kifu can add it to his QA suite. And then this D3N caching thing, that got reviewed by a couple of people and then has had updates based on that review. That's still in review and will be in testing, assuming everything looks good. Um, and then Radic is still, I think, looking at Ma Jianpeng's reduced buffer list rebuild PR in BlueFS, trying to do that more generically than just in the BlueFS code. So he's working on that still, I believe. And that was it for updated PRs. So I already basically talked about the buffer list append stuff. So should we move on to talking about Crush?
Yeah, can do.
Excellent, cool. Yeah, I'm excited to hear about this.
All right, so let me just quickly first link what I'm talking about in the chat so people can take a look. So this week I came across a paper published at the FAST conference, 5 months ago, I think, back in March. And this paper talks about sort of like an expansion to the Crush algorithm. So first they discuss some weak points of Crush in the case when there's a cluster expansion and then there's a lot of data migration happening. And that was basically their motivation to making that extension to Crush. And the idea is making sort of like a centralized authority responsible, in addition, responsible for the data migration in the cluster expansions. So those were kind of like that was the main idea, and they introduced a number of ways to handle the load balancing. And at the end, they talk about some of the results they got, and it seems like the algorithm they introduced is achieving much better results than Crush. They were performing the test on Ceph and RBD. So I saw it like 2 days ago. So there's still I still need to go over it more, but I kind of wanted to use this meeting to show it to you guys and give you time to go over it if you want to and tell me what you think about it.
So yeah, thanks for from a high level. Oh, go ahead, Josh.
I hadn't seen this before myself, and it looks very interesting. I'll have to read through the paper to kind of understand what's going on here. If you've already looked at it a bit, is like the main idea that they've kind of reduced the amount of data being migrated, or that they're spreading the migration over a longer period of time, or?
Yeah. So the idea is they are reducing the amount of data migrated because they are adding another virtual sort of layer under root. You can see there are multiple figures in the paper. So they're adding a virtual layer. So they're looking at the different shelves and cabinets as layers. So when you make the expansion, it doesn't affect the weight of the other layers, and then you don't have the migration happening. So when you have new data coming in, it only goes to the new layer. And then they are discussing how they are handling the load balancing, because there's sort of a trade-off there. And they are presenting three methods, namely PG remapping, cluster shrinking, and layer merging. So, yeah.
Okay, so it's kind of
that answered your question
differently than old data to avoid moving too much around.
Yeah. So they are. So yeah, exactly. So they are using this. I have it here. 1 second. They're basically timing. They're adding like timestamps. They're calculating the time that the data is coming in, so that they can distinguish between old data and new data. So when you're doing the expansion,
is the idea then that new data is always landing on like OSDs that they won't have to go back and then do like future migration for, or is it how is it? I guess I'm still trying to understand how what are the bounds on data migration, like for new data and old data? Does it change that?
Okay, so
I assume.
so yeah, so I didn't go into specifics of like their exact calculation of what do they determine as old data and new data. I kind of went over like the main idea and the results. So the main idea was, like I said, doing those timestamps and
Yeah.
adding a virtual layer under the root, kind of grouping all the cabinets and shelves in a virtual layer, so that when you expand, for example, you add another shelf, then it only affects that virtual layer, and it doesn't affect the weights of the other layers. So then Crush doesn't do the load balancing, or MapX in this case, which is the extension to Crush.
Yeah. I need to read through this probably in more detail to really understand what the ramifications of that are.
Yeah. There's definitely a lot. There's definitely a lot to read. I myself, like I said, I came across that just 2 days ago, so I thought this will be a good forum to bring that up, to give everybody who's interested, give them time to go over it. I'll definitely look further into that as well before next week's meeting, and then next week we can all kind of have a better idea of the entire paper, and we can discuss it further if that is something you're interested in.
Yeah, absolutely. Very interesting. Josh, what do you think about the claim about, like, I think they said specifically unbounded data movement? Maybe uncontrolled data migration is what they say, I guess.
Yeah,
Yeah.
I think that's one way to describe things. I mean, it's certainly controlled in some sense, like that there's a bounded amount of data that's being moved, and there is control over how fast it moves outside of Crush itself.
Yeah.
But it sounds like they're kind of describing it being uncontrolled in the sense that it's not directly controlled just by Crush.
Yeah, because I looked at that and I was like, well, I don't know.
Yeah, they're saying that it's basically like Crush is using like a decentralized placement methods, and they are sort of adding like another centralized authority once cluster expansions are happening, and they are showing that once you add that centralized authority, you don't hurt the load balancing. So that's good, but at the same time, you're also getting better performance because data is not migrating over between the different layers. Yeah, that's kind of the idea.
Yeah, I think I'll have to read more to understand the trade-offs involved, like if it has potential implications for the failure domains or kind of the balancing of IO load as well.
Yeah, definitely. That's the reason why I thought I'd bring that up here.
And when you were reading through this, did it sound like for new objects, do we end up? What happens to new objects? Like while you're in a degraded or recovery scenario, what is the effect on new objects when they come in with this scheme versus traditional Crush? Did you see anything on that, or have you not gotten that?
I'm not sure I've seen something. I'm not sure I've seen either they didn't address it or I just didn't notice it.
Okay. Okay.
But I think that in section 3.2, when they are talking about migration control and they're kind of introducing the the three methods they are using to address the potential load imbalance between the layers, I think that the answer to your question might reside there. I'm pretty sure.
Okay.
I just didn't have enough time to really go into detail.
Yeah. No worries. No worries.
But I just thought the results were pretty surprising. That's why I thought it would be pretty interesting to have a look at that, because it seems like the results are significantly better in terms of the IOPS they are getting and the latency.
Yeah. Yeah. Did they say in here what their test setup is?
Yeah. In section 4, you have evaluation, and they are describing both the machine they are using, they are describing the cluster, the storage devices, stuff like that, and they're saying the Ceph version, which is Luminous.
Yeah. Yeah, it's Luminous with 4 5.5 terabyte hard drives, and they don't mention any NVMe or SSD storage.
No, it doesn't seem. It seems like they were doing the test on HDDs.
Yep. So
Well,
that's
seems like kind of the best
interesting,
case for their algorithm, right? I mean, that's
Exactly.
the case where it would be most expensive to recover.
Yep. So the question is, right, like if you did this test on SSDs, if it'd do anything at all, or if it would just, the background IO would matter.
Yeah, the thing is that the way they described it, it seems like implementing their algorithm was pretty easy. So in the case that they didn't run it on SSDs, maybe we can test it ourselves and see how it performs.
The other thing is just kind of the impact they're trying to reduce on client I/O lower left something with the work on quality of service, where we're balancing client background I/O versus client I/O as well, and we wondering how much of the kind of impact of this would already be captured by a better quality of service.
Yeah, I get what you're saying. So that's why I think that it's worth to go into more detail, like read through it again, and maybe even try to recreate their tests on different hardware, and kind of see the results. I don't think it should be that complicated because they didn't completely change Crush. They sort of like just extended it. So yeah, I'll take a look into that.
That'd be really interesting. Do you have hardware you can test on?
Me personally, no, not really.
Okay. If you decide you want to do this and like really, do it for real, let me know. We can probably get you on one of the Inserta nodes so that you can test with hard drives and NVMe drives.
Okay. So I guess we should discuss this further like next week once everybody, or I don't know, in 2 weeks once everybody in the call has some time to go over it if they want to. So then we will all have a better sense of exactly what is going on in the paper, and see if there are any like potential issues there. What do you think?
Yeah, sounds great. I think I certainly we will take a look and try to get a better understanding of the trade-offs involved. Because with data placement like this, there's always trade-offs.
Yeah, sounds good.
So I mean, I guess one thing here, right, would be that they talk about performance, but really what we want to know, or at least what I want to know, is with like this migration-free expansion and avoiding migration in general, what's the reduced amount of data movement, right? Because performance, I don't really care about. I mean, that's kind of arbitrary, but what's the real effect on data movement in the cluster? That's what I really want to know. I don't know if they actually show that, do they?
I see here a figure talking about the number of affected PGs. Number of affected PGs in layer merging. So after 4 expansions of the cluster. I don't see here anything specific to the percentage of data migrated, but they might have like just wrote that and didn't add like a graph or something. It might be discussed in one of the sections. So
it's just it surprises me that they don't have a figure showing the reduced data migration, given that that's like the whole, as far as I understand it, the fundamental benefit of this is that I don't care about latency or IAPS in the grand scheme of things that much. For this specific thing that they're doing, I want to know what's the reduction in data migration because of it.
Yeah, the idea I got from them from the beginning of the paper was that they are more interested in the effect that reduced data migration would have on stuff like IOPS and latency. So that I'm assuming that is why the figures they supplied were mainly discussing about those sort of things, IOPS, latency, and all the rest of the things we have here. The computation overhead and stuff like that.
I mean, that's all kind of nice, but that comes as a result, hopefully, of the reduced data migration and the reduced data migration. The big reason why I like that potentially more even than IOPS and throughput and all these other benefits, latency, is that especially on NVMe drives, you have a reduced amount of write endurance, right? You have a limited amount of write endurance. And so if during healing events you can reduce that, you can make your NVMe drives live longer.
Yeah, exactly. I guess I will try to, it's hard to me to believe that they didn't supply even like some sort of number of the reduced migration. Maybe they didn't dedicate a full figure for that. But I do believe that they somewhere mentioned the reduced migration, but that is just me hoping. I'll have to search for that.
Yeah, I mean, I'm kind of doing a keyword search for migration through the paper right now, and I see lots of mentions of it, but it's always in terms of things like the migration may never happen, or less migration, or reduced migration. It's like kind of wishy-washy.
Yeah, if you take a look at figure number 2. Before they even discuss MapX, I think this shows like the data migration in Crush. It's figure number 2.
Let's see. But sorry, what page is that on?
Like one of the first pages.
Just on
page
is it that?
number
I see it there.
4.
Yep. 3? Figure 2.
Yeah, 3. 3. Yeah.
Okay. Yeah. Okay, so they're saying that this is when you've got a large cluster of 10,000 OSDs and you add a rack of 80 OSDs, 5 5.86% of the PGs are affected, but if you have a small cluster of 240 OSDs, then 59% of the PGs are affected. Josh, do you remember in the Sage's Crush paper, we have limitations on data migration?
Yeah, they discuss it in the paper. I think I know what you're talking about. It's called there's a there's a variable called OSD max or OSD's max backfill. I think I'm trying to grab that. I'm pretty sure they mentioned that that Ceph has some sort of variable limiting the migration happening, and they do address that in their experiments actually. And they show that even with that sort of optimization, their algorithm still outperforms, once again, in terms of IOPS and latency.
Yeah, that max backfills is about the rate of recovery, not about the amount of data moved. I think, Mark, what you're talking about maybe is more related to kind of the modulo stuff in Crush to try to limit migration to like half a subtree.
Yeah, exactly. It's been a while, a long time since I really looked at this, but when I was trying to make like a Halton sequence based distribution algorithm that it ultimately just didn't work. It was one of the big problems with it is the amount of data migration. I thought, if I remembered right, in Crush, one of the big advantages is that you had a bounds on how much data migrated when you removed or added a target.
Yeah, that's right. I just don't remember the precise bounds on what that is. But I think it can have more of an impact on a smaller cluster for sure, just because you are usually changing a larger percentage of the cluster at a time.
Yeah, so you have like a bound on adding any one, and then it must like have a cumulative effect where like this 59% number that they came up with for like 80 OSDs in a 240 OSD cluster, it must be that 59% is the cumulative like change when you do all of these together. Does that make sense?
Yeah, maybe. I mean, like 80 out of 240 is like an increase of a third, right? So it's going to be a much larger impact than adding 80 OSDs to a 1,000-node cluster.
Yeah. So I don't suppose, do they have a graph in here that shows that specific example compared to what then they do? How many PGs were affected?
I'm pretty sure. Let me take a look. I think it's at the end of the paper.
There's this thing on page 7, I guess.
Yeah. There is the figure number 8. Yeah, in page 7.
Yeah.
It talks about the different experiments, and then I'm not sure.
It says
yeah.
I mean, it says number of PGs affected, but what was the configuration for that, for figure 8? Like, how big of a...
I think, are you talking about the experiment setup?
Well, what I want...
Go ahead.
Well, what I really want is I want that result from figure 2, adding one rack 80 OSDs to 240 OSDs. I want to see the Crush result, and then I want to see the MapX result. That's basically what I want.
Yeah. Okay.
So I'm trying to figure out, like in figure 8 now, what exactly that means. Like, what's the comparison here?
you're gonna have to read through where they discuss about layer merging in section number 3, 3.2 to be exact, to really, I guess, understand what they're comparing there.
Yeah. This, I mean, it's not like a one-to-one comparison of what's in Figure 2. It's something different, right?
Yeah.
By the way, it's worth
I mean,
noting
for
that
others, I can contact them if.
yeah, the authors here are active in the Ceph community, so I'm sure they'd be willing to answer questions and may even be able to share their code if you wanted to run more experiments or extend their work.
Yeah.
Yeah.
What do you think about having them, if they're active? I mean, maybe they could come present to us.
Yeah, maybe. If you like, I can reach out to them.
I'm open. Amnon, what do you think? Would you be interested in that? Would it be useful for you?
Yeah. It would be really useful because the thing is, in the conference, they were supposed to also present their work in the conference, but they couldn't make it because of coronavirus. So it was just somebody else just reading their slides. So you couldn't really understand anything because he was just reading the slides. So I think they would also be interested in presenting that. I know I would definitely. So I mean, I can contact them or Josh can. I don't really mind. Whatever you feel comfortable with.
Yeah, it doesn't matter to me. Whichever you guys want to do, just let me know and we'll set up a time slot on one of the performance meetings for it.
Yeah, sure. If you want to reach out to them, that sounds great.
Yeah, cool. I can do that. I'll send them an email today.
Cool. Yeah, just let me know when, and we'll reserve it for them.
Yeah. Okay, sounds
Cool.
good. And then we between us we can talk about it more next week, I think.
Yeah.
Once we read more through the paper.
Cool.
Yeah, sounds great.
All right. We've got a lot of latecomers from the course stand up here. Any thoughts or questions, folks?
I think I need to read through the paper to ask more questions, so I'm going to.
Sure. All right. Well, then let's all read the paper in more detail this week, and then next week we'll talk about it. Oh, there's a chat.
The link I just attached has it has a link to the paper itself and also to the presentation video from the conference if anyone is interested. But once again, like I said, the person presenting is he's just like reading the slides because he's not one of the people who worked on the paper because they couldn't make it to the conference. So.
Okay.
But if you want more slides, there you go.
Cool. This thing here. Okay, cool. All right. Well, anything else this week then, guys? If not, then have a good week and looking forward to discussing this more next week. Have a good one.
Have a good week. Bye-bye.
Later.
You too.
See you later,
Thanks.
guys.
Yeah.